Look around today, and it feels like we're surrounded by artificial minds. Chatbots are drafting corporate emails and building complex software code in seconds. It is incredibly easy to look at those instant, articulate responses and assume there is a thinking brain on the other side of the screen, reasoning its way through your prompts. This diagram shows the mechanical reality. There is no actual thinking happening here. Large language models are executing a high-speed game of fill-in-the-blank, calculating the mathematical probability of what the very next word should be. But guessing that single next word with any real accuracy requires building one of the largest and most complex computing systems ever devised. By repeating this simple calculation across a massive digital infrastructure, the system begins to produce results that appear increasingly indistinguishable from human writing. To make an accurate guess, the model needs context. Engineers provide this by building a foundation model, which involves feeding the system a staggering amount of unlabeled, self-supervised text from the internet so it can learn language patterns on its own. To understand what qualifies as large in this context, we have to look at the specific way computers measure and store human language. This block represents 1 gigabyte of text, storing roughly 178 million words. Combine 1 million of these blocks, and you reach a single petabyte. This chart shows the specific 45 terabyte slice of that data used to train the GPT-3 model. This massive ingestion of text provides the raw statistical evidence the model needs to eventually recognize patterns and predict human language. Holding petabytes of text is one thing, but processing it to find those patterns requires a specific architecture known as a neural network. In the case of GPT, that network relies on something called a transformer architecture. This web shows how a transformer reads. It draws mathematical connections between every single word simultaneously, evaluating how they relate. Weighing these connections at once, the system organizes into a matrix, plotting the sentence's structural meaning. Without this architectural ability to map out context, the datasets we discussed would be a useless pile of words. The transformer is the engine that makes prediction possible. When the engine starts training, its first attempts are completely blind. If prompted to complete a sentence, it might spit out a random guess like, "the sky is bug." To fix errors like that, the model uses parameters. These are independent internal values the system can turn up or down whenever it spots a difference between its guess and the actual correct text. This graph tracks the training loop. The model tweaks 175 billion parameters, shifting values to force the error margin down. As the error rate hits 0, it locks in the reliable prediction: the sky is blue. Machine learning is the result of millions of these mathematical micro-adjustments, systematically filtering out incorrect answers until only the right one is left standing. Once that generalist foundation model knows how to predict text, engineers run it through a process called fine-tuning. They expose the model to a much smaller, highly specific dataset. This focused secondary round of training forces the model to refine its vocabulary and become an expert at a single, dedicated task. That specialized training is how businesses deploy this technology today. A fine-tuned model becomes an intelligent customer service chatbot, resolving specific complaints, or an automated engine drafting targeted social media posts. It even applies beyond text writing, directly into software development. The same predictive math that finishes a sentence can be fine-tuned to generate, review, and debug complex lines of code. These sophisticated business tools are the final output of 3 distinct components: massive data, transformer architecture, and an iterative training process that systematically refines its own accuracy.